Okay, gang, now it's time to talk a little bit about design synthesis. Now, synthesis is a fairly new term for folks who aren't been around VHDL or the FPGA world. And it basically is quite simply taking a design and mapping it directly to hardware. So the idea being you're going to describe hardware in words, and then a synthesizer is going to read those words and interpret them in terms of gates and registers and multiplexers and all kinds of other devices inside your digital design. So that's what a VHDL file does. It describes a digital design, and then you synthesize the design onto an FPGA or a CPLD or some other programmable device. So that's kind of the idea of the whole design synthesis. Now, one of the biggest problems that we have with new people to this area of study is the confusion of the word programming, and the fact that they think in terms of programming a device, like I'm going to be programming an FPGA or I'm going to be programming a CPLD, and they confuse that with the term programming a microcontroller or a processor. So those are two incredibly different things, and we're going to talk about those different things and why they're so different in this video, and talk about the design process and kind of what goes on during synthesis. So what we'll do is let's start with looking at computer language. And I call this programmable confusion because it is difficult for people who are used to the programming world to understand what's going on. In fact, one of the biggest mistakes people make in designing with FPGAs and programming in VHDL is the fact that they try to look at the FPGA sort of like they look at a processor, and they write it as if they're writing a program, a sequential program for a processor, and they're completely different things. And so you can create some very inefficient hardware if you aren't aware of how things work internally. So that's one of the things that we're going to do in this video series, is carry you through the process of how to write efficient VHDL code directly targeted to hardware. Now, if we take a look at this, you'll notice, let me get my tools up here. You'll notice that we start with a code, right? And so in this case, in a computer, we would write code in, say, a language like C, C++, even an assembly language. You know, any computer language you're used to writing sequential code in would apply to the code section. Then we go through a process of compiling the code into machine code for the specific processor we're targeting. So this all happens behind the scenes for most development systems. You write your code, you hit compile, it runs and runs and runs, and then you download the program to your device. But what it's doing is it's creating an intermediate file called a machine code file. And inside that file, it has machine code instructions for the specific processor that you're targeting. So the compiler goes through a lot of iterations of figuring out how to translate this into numeric codes for the processor, and that's your executable file. And so from there, what ends up happening is you take your microcode and then you basically load that into memory. Okay, so you load your microcode into memory. So the idea is you write code first, you compile it into machine code, you load it directly into the memory of the device you're using. So this is whatever the computer hardware is that you're using. And then the core executes the program for you one instruction at a time. So here's the big deal here. We're fetching one bytecode instruction at a time. Sorry, one machine code instruction at a time. I'm confusing that with intermediate language like Java. But anyway, it takes a machine code, and then it takes the machine code and reads it into the processor core, and the core executes that code based on how it's been pre-designed. So the key here, and this is an important factor, is this whole fixed core thing. This right here, the fixed core, is fixed hardware. it doesn't change. It is a fixed set of resistors, some ALU for handling numeric computations, bus structures for transferring data, register structures for storing intermediate information. But at the heart of it is pre-designed core, and it's fixed. It doesn't change. And so what happens is you're reading in machine code instructions into the core, and then the core executes those one at a time. And so that's the big deal here. This is a continuously fetched operation. As the program runs, as the hardware runs, it's continually fetching new instructions and in continually interpreting those new instructions. And that is where your kind of bottleneck occurs in processors. The idea that you're constantly having to read instructions one at a time and then processing those instructions. Now we have more sophisticated architectures that allow for multi-cores, and then there's some parallelism, things that we can use. Pipelining can help efficiency and fetching, and then you've got the parallel processing where you can break off. But it all boils down to a core can only execute code one instruction at a time, and it continually fetches that. And therein lies some inefficiencies. If you're constantly having to fetch instructions and you can only give them one at a time, that slows the process of some systems down, right? And so FPGAs and CPLDs have the advantage of being programmable as a parallel processing. So you can create multiple parallel paths and do things simultaneously, whereas in a core you have to do them sequentially. So let's take a look at this and then go to the idea of a synthesis language and what's going on in a synthesis language. So this previous one was basically a computer language. So we're going to take a look at what is a synthesis language. That's what VHDL is. We start with code just like before, and then what happens is we actually synthesize based on that code. So we take that code and we convert it into a bit stream, a bit file, and that bit file has ones and zeros in it that are designed to enable or disable parts of our chip, like the FPGA. So this machine, nope, that's not machine code, I need to fix that, but that's this is a bit file. That bit file is written to the CPLD or the FPGA one time. Okay, one time. So instead of machine code, this should be bit file, and that should be a bit file. And so that is written to an FPGA or a CPLD, and that CPLD then gets configured immediately with a different hardware configuration. So think of this as sort of like a whole bunch of building blocks, and then your code is showing how to connect those building blocks up to one another, right? So there's predefined entities inside there, such as multiplexers, some combinational logic elements, some registers for storage. There's all kinds of elements built into the FPGA already that pre-fabricated inside the FPGA. Your code is basically saying, I want you to hook this register up to this bus, and then I want this signal to be connected to that multiplexer input. So you're basically telling it how to hook up existing hardware in the chip. So that's very, very different than a sequentially executed process, because here's the key. You program this one time and it's fixed, it's done. There is no fetching of instructions like you do in a processor. It's fixed, it's hardware. You're basically describing hardware design. And so when you synthesize your design of VHDL, you are laying out a hardware design that will stay fixed as long as the power is applied to the chip. Now, some chips are non-volatile, which means that once they're programmed, they stay that way for a long time, even if you take power away. Like CPLDs actually do that quite well. But we'll talk about those in later videos about the differences between FPGAs and CPLDs. The idea is the same, though. They're programmable. You have a bit stream of codes that basically allow you to program them. And in later videos, I'll show you the architecture internally of a CPLD and of an FPGA and how these bit files actually do the programming. In fact, we'll be doing some synthesis of our own where we design the bit stream to program the core or program the FPGA cells to do the synthesis for it. We'll do the synthesis for it, and it will lay that out in hardware. So that's really some pretty cool stuff that's coming. Before we get there, though, let's talk a little bit about synthesis and the technical definition of synthesis. Basically, it's moving, if we look at synthesis at its core, it's basically moving from a higher level of abstraction to a lower level of abstraction. So the idea is, the word synthesis means you take this high level abstraction and then you move down to more detailed level, okay? So a good example of this might be, for instance, RTL synthesis, which is a very, very common synthesis in most of these development systems which synthesize VHDL code, right? So it's basically, RTL stands for register transfer level, and then basically the register transfer level, it organizes things in blocks, register type blocks for storage. And when we do a RTL synthesis, we are reducing all of our design, or our high level description, down into individual register blocks. Gate level synthesis is basically reducing your design down to just gates. Now, you know, in digital, you can describe anything combinational logic wise as gates, any logic gates and or that kind of stuff. Add in a flip-flop or two and you have elemental storage, and therefore you have a complete digital system. Could be described as a series of gates and flip-flops, and that's it. So every digital system can be described that way. It gets complex when you get more complex systems, but it works. That's how everything can be defined. Now, when we talk about technology mapping, we're reducing it down to a specific technology. So when we talk about technology mapping, we're reducing things down to a specific technology, sort of transistor level and that kind of stuff. So we're really getting low. So synthesis is going from that high level down to that lower level. So to talk about the idea of synthesis and how it works, let's talk about different levels of abstraction, because we're going from a high level to a low level of abstraction when we synthesize. So what are these levels of abstraction? So transistor level abstraction is basically things at the transistor level, which makes sense. Gate level, reduce everything to gates. Register transfer, that reduces everything to larger blocks like multiplexers and registers. And then processor level is a really higher level of abstraction, where you don't really worry about the individual gates, but the overall functionality of the processor. So if we dig deep into this, we find that for transistor level, like we said before, we're talking about things like the transistors, the resistors, even a capacitor or two. So all of those are factors inside here. It deals in voltages and currents. So we're really getting low when we're getting down to transistor level abstraction. Time is a continuous function. You sort of think of an oscilloscope where you can see signals rise and fall, time, slew rates, that kind of stuff are all part of the transistor level abstraction. And we can define this performance as differential equations, as we've learned in our earlier education as far as electronics are concerned. If we move to gate level abstraction, we have moved up to a higher level of abstraction. We're talking now about logic gates and flip-flops. And like I said before, everything can be described as logic gates and flip-flops in the digital world. And so if you look inside FPGAs and CPLDs, you're going to find that they have already pre-set up logic gates and flip-flops for you to connect and hook up with your code. And so that's what we're going to really dive into details in the later videos. And then for the signal types, we talk about highs and lows. We don't talk about voltage levels and current. We're talking about, is this a high or is this a low, a 1 or a 0? We also talk in terms in the time era of prop delay. When we change an input signal here, how long does it take to the output signal to happen? And that's generally when we're talking about timing parameters, that's what we're talking about, how, the propagation delay through the circuits. And then basically in the descriptions in here, this can actually be described as not differential equations. I think I made a copy paste here error, but this is more like Boolean expressions and stuff in here. So this wouldn't be differential equations. This would be more like the Boolean expressions. Okay. Then when we get into the next level of abstraction, we'll be talking about things like adders. So as you can see, as we go to the next higher level of abstraction, what we're seeing is a move from more fine detail to a higher level look at things, right? So instead of us worrying about the individual transistors and other things in the circuit at the at the transistor level, when we move up to the register transfer, we're thinking in terms of adders and multiplexers, bigger picture blocks, registers, that kind of stuff. And so that becomes our level. We talk in terms of signals like state values or integer numeric values, these kinds of things, right? So a grouping of 32 bits would be considered an integer inside a register transfer level abstraction, or it could be. There's lots of ways to look at it, but it could be. In timing, we're talking about clock edges, right? So we're clocking our system. We have a rising edge. We're looking at the timing of that and how that progresses through the system. And we can describe this in terms of finite state machines, so like a machine that shows how it executes and works from one sequence to the other. So finite state machines there. Going even higher, we can talk in terms of the processor level, where we talk about the processor core and memory structures, right? So internal RAM, caches, that kind of stuff. And we basically can start talking about more abstract data types like a floating point or a double precision numbers and that kind of stuff. So we're really stepping away from the individual transistors now, because those are way down in our level of abstraction. And then we talk in terms of continuous function, like execution times and that kind of stuff. And we describe it in high-level languages like C and Python and the works like that. So this is the different levels of abstraction that we have in our digital design world. And when we synthesize, we go from a higher level of abstraction down to a lower level of abstraction. That's what it means to do synthesis. So and there are lots of different synthesis processes, right? So typically in our code, we'll be starting off with a, say an RTL description. After writing, the VHDL will be translated into an RTL description, and then that will be translated into mapping inside the hardware. So we need to talk a little bit about the physical design now, because we've talked abstractly about how you can describe designs as gates and transistors and processors and registers and that kind of stuff. But now we want to look at this from the standpoint of the physical, the actual physical mapping of our system. So in physical design, we're basically talking about two things. There's the floor planning, which maps the elements to the device resources. So when we are writing VHDL code, we write it as generically as we can to describe our digital design. The synthesis tool will translate that design into RTL, and then RTL will be then mapped using a floor planning tool to the actual resources on a particular FPGA or a CPLD. So it just maps it from those RTL descriptions down into the physical actual hardware of the device. So every vendor has its own synthesis tool. Xilinx, for instance, uses Vivado, and that tool basically understands all the hardware that they have in their catalog, and then they know how to map it to those specific elements in that particular hardware. If you're using an Arctic 7 FPGA. It understands how the cells are built inside the Arctic-7, what the flip-flop resources are, what your lookup tables are. All of that's already pre-known by the developers, so they know how to map that to physical hardware, which we'll learn about a little bit later. So don't worry if you don't know those terms. That's something that's coming up down the road. And then we have the gate level synthesis, which talks about path links and electrical characteristics. So when we start mapping to actual hardware, it becomes important for us to understand propagation delays from one part of the design to another. Oftentimes we'll refer to things as a combinational cloud, right? So you have inputs feeding into the cloud, and then a few nanoseconds later you'll have outputs coming out of other signals, but it's not instantaneous. And that can affect how quickly you can clock your system. This designed for the FPGA, so that can have a real big impact there. And it can also affect the types of things you can do with the system, and we'll talk more about that as well later. So let's go back through and look at as a summary, the developmental flow of the whole process, right? So, and this kind of goes back to the beginning when we were talking about how to design using VHDL in our introductory video. So first thing you want to do is develop a design file. Now this can be done in a language like VHDL. Another language like Verilog is also very popular out there. So those two are the main competing languages, but this series is basically focused on VHDL. We want to also go through the process of developing a test bench. And the test bench, if you remember, is designed to allow us to go in and test our design to see if the design's working the way we expect it to. We'll then go through and simulate our design using a simulator. Typically the simulator is provided by the manufacturer of whatever chip you're using, and you can run it through some simulations using your test bench, look at the output signals to make sure they match up with what your expectations are. Then, once you've done that, you can actually simulate with more accuracy. So what this means is your first simulation tends to be a behavioral or a logic simulation, which is simulating the design as you've described it in words, in generic terms. But then you need to kind of understand how the device has been mapped to hardware to understand what your actual timing constraints are, right? So you can simulate at a timing level, which will tell you, okay, how fast are the prop delays in the system, the way it's been mapped and the way it's been routed. And then, I jumped ahead there. The way it's been mapped to the actual resources in the design. Then we can go through a place and route, which basically takes that and maps it to actual locations on the chip. So in the first place, we know the chip has thousands and thousands of these blocks or cells, okay? Each cell has some combinational logic and some storage elements in them. And so we know that, and so we can kind of simulate timing based on that when we map the RTL, which is a generic description, to the actual hardware available in that particular chip. But then we go through a place and route, which takes that and maps it to actual locations on the chip. So if you've got a very large chip, the one you might map it, the macro cell in the far left corner of the silicon substrate, and then you might map that to the one next to it, and that may have to jump over 5 cells to the next one. That means it routes through this signal. So you're really laying it now on the actual FPGA device. You're programming its connections on the device, which means now you have much better data about how fast the signals will propagate and what your clock rates are actually going to be. So you can do yet another simulation and timing analysis. Now, we may do some of this later. It's a pretty advanced simulation to go down into the timing and look at that, but we may actually play around with that later. But our focus right now is really going to be behavioral, understanding and making sure it works properly. And the behavioral is pretty good at predicting the performance of the system. In order to program the chip, though, and use the FPGA or CPLD in your design, you have to know the pinouts of each of your ports. Okay, so if you're creating an FPGA and you're going to drop it in your design and you've got a bunch of inputs connected to it and a bunch of outputs connected to it, you need to know which pins to connect your output, your external stuff to, and that's what the configuration file is all about. So a configuration file maps your internal design ports to physical pins on the actual chip. Okay, so that configuration file is a very important part of the design process. Now, most of the time when we have these development boards that we'll be using, like the Basis 3, it's already predefined for you, so you don't really have a choice of how to route it because or how to connect it, because it's already connected on the actual physical board. You can't change that. If you're doing an actual design from scratch, though, a lot of times it's better to wait on mapping to the pins and let the tool do it for you based on how the design was laid out on the chip. So there's a lot of factors involved in picking just the right way to do that, and so that's definitely something that we want to definitely look at later. And then you go to the process of programming the device, and that's a fairly easy step in most of these tools. The device can be easily programmed by the press of a button. It downloads right into the chip itself, and then boom, you're off and ready to go. And so we'll see we saw actually some examples of that in a previous video where we downloaded our bit file directly to the Arctic 7 FPGA and the Basis 3 board, and we saw it play around with the LEDs and the switches that we had there. So that's kind of the tour of the design synthesis. And this is the whole idea behind VHDL, is to be able to describe in words a design and then drop it into hardware. So that's it for this video, and see you guys in the next one.